Assalamualaikum and good day. We are looking at chapter 11, rolling motion of a rigid object. So when we talk about rolling motion of a rigid object, we are talking about the axis of rotation which is not fixed in space. We also have assumption. First one, we treat the motions of the rigid object rotating about the moving axis. Secondly, we discussed about a homogeneous rigid object having a high degree of symmetry such as cylinder, sphere or hoop. We also assume that the object undergoes rolling motion along a flat surface. And finally, an object such as a cylinder rolls without slipping on the surface, where we call it as pure rolling motion. Suppose we have a cylinder which is rolling on a straight path. The center of mass moves in a straight line, but a point on the rim moves in a more complex path, which we call it as cycloid. So this is the cycloid path, okay? And this is the center of mass which is moving in a straight line. Okay, consider a uniform cylinder of radius r rolling without slipping on the horizontal surface, which is in figure 11.2. And as the cylinder rotates through an angle theta, its center of mass moves with a linear distance s, where s is given by r theta. So, the linear speed of the center of mass for pure rolling motion is given by Vcm equals to ds over dt, where s is r theta, where r is a constant value where we can put it outside the differentiation. Then we have d theta over dt. So, d theta over dt is omega. Omega is the angular velocity of the cylinder. So, v Cm is equals to r omega. And when we talk about linear accelerations of the center of mass for pure rolling motion, we have Acm equals to the differentiations of Vcm, where Vcm is r omega, r is constant, we put it outside the differentiation, so we have d omega over dt, which is equals to r alpha, where alpha is the angular accelerations of the cylinder. And the equation 11.1 holds whenever the cylinder or sphere rolls without slipping and is the condition for pure rolling motion. Okay, let's look at this figure 11.3, where we have a cylinder. Okay, the cylinder is rolling, and in a short time after the moment, we can see that the rim point P is moving from 6 o'clock position to the 7 o'clock position. Same also goes to point P, where it will move from 10 o'clock position to 11 o'clock position. Okay, again, look at this figure. Okay, so we have all points on the cylinder have the same angular speed. But at point P prime, since it is a distance twice, okay, the distance from P prime to P is twice the distance from P to the center of mass. So P prime has a speed 2 Vcm equals to 2r omega. So the linear velocity of any point is in the direction perpendicular to the line from that point to the contact point. For example, from point P to this point, this is the point where we have the speed direction is perpendicular to the line that is contacting the point to the point of contact P. And the center of mass move with linear speed Vcm, okay, while at point P the speed is equals to 0. So point P we call it as contact point. So at any instant, the part of rim that is at point P is at rest. relative to the surface because slipping does not occur. Okay, let's look at the pure linear motion. So each point on its move to the right with the same speed, which is the VCM, okay, the speed at the center of mass. And if we look at the pure rotational motion, each point on the cylinder has the same rotational speed omega, but at the center the speed is 0 and it has axis of rotation. But if you look at rolling motion is actually the combination of translational and rotational motion. So at point P prime, the speed is the combination of the linear speed and also the rotational speed, which is equals to 2 VCM. At center of mass, the speed is equals to the speed of the center of mass, while at point P, at contact point, the speed equals to 0. For total kinetic energy of the rolling cylinder, we have K equals to 1 over 2 IP omega square, where IP is the moment of inertia about a rotation axis through P. And if we apply the parallel axis theorem, we can substitute IP equals to ICM plus mr square into equation 11.3 to obtain K equals to I over 2 ICM omega square plus 1 over 2 mr square omega square. So this is actually if we replace VCM equals to R omega. Okay, so we will have equation 11.4, where this equation is actually the combination of the rotational kinetic energy of the cylinder about its center of mass and also the kinetic energy of the cylinder would have if it were just translating through space without rotating. And for the conclusion, we can say that the total kinetic energy of a rolling object is the sum of the rotational kinetic energy about the center of mass and the translational kinetic energy of the center of mass. Okay, let's look at this figure where we have a sphere, or it can be also cylinder or hoop, rolling down a rough inclined surface, and the rolling is without slipping, and the sphere is released from rest at the top of the incline. Okay. So the accelerated rolling motion is possible only if a frictional force is present between the sphere and the incline to produce a net torque about the center of mass. Despite the presence of friction, no loss of mechanical energy occurs because the contact point is at rest relative to the surface at any instant. It means the energy is still conserved. If the sphere were to slip, mechanical energy would be lost as motion progresses. Okay, so using the fact that VCM equals to R omega for pure rolling motion, from equation 11.4, if you still remember, we can replace omega square with VCM over R. So this equation will be rearranged, become K equals to 1 over 2 ICM over R square plus M, and then VCM square. Okay, so this equation, we use the conservations of energy, which is Ki plus Ui equals to Kf plus Uf. So we will have the energy at the top of the incline, and here the energy at the bottom of the incline. We rearrange this equation. We have the speed of the center of mass for the rolling sphere, which is given by equation 11.6. Okay, let's look at this example. For a solid sphere shown in the figure below, calculate the linear speed of the center of mass at the bottom of the incline and the magnitude of the linear accelerations of the center of mass. So we apply the equation that we derived just now, which is equation 11.6, and you replace ICM with the ICM for a sphere, moment inertia for a sphere, which is 2 over 5 mr square, and you rearrange this, you solve, you got the square root of 10 over 7 gh. So this is the answer for the linear speed of the center of mass. And if we want to calculate the accelerations of the center of mass, by taking the equation here, we square both sides, and h is replaced with x sine theta. Okay, we use the kinematic equation. V initial equals to 0 because it is released from rest, and the equation finally become this accelerations of center of mass equals to 5 over 7 g sine theta. But let's look at the same example, but this time we use a dynamic method, which we look at the energy consideration. Okay, we should get the same result as the previous example. What we do is we draw a free body diagram. Okay, we have normal force, we have a gravity force, and gravity force as x component, y components, and also friction force. And we use the equation for torque because the object is rolling. So torque equals to I alpha, and the one that make the rolling motion or produce the torque is actually the friction force, and R is the moment arm. Okay, alpha as angular acceleration is replaced with ACM over R. Okay, and then we have I for the sphere, which is 2 over 5 mr square, and we cancel all the r, and we have the expression for friction force, and we apply to the Newton's law in x direction. So we have mg sine theta minus f equals to ma, and you substitute f into this equation, and we cancel all m. Finally, we have the expression for accelerations of the center of mass 5 over 7 g sine theta, which is the same as our previous example. So that is all about rolling motion. Thank you.